Hello and welcome everyone. My name is Hannah Mason and I'm a technical editor at Composites World. I want to thank you for joining us today for this webinar titled Advanced Thermal and Fire Protection for Aerospace and Automotive Applications with LMPAEK Unidirectional Tapes, brought to you by Composites World and presented by Victrex. So as you can see, we have three presenters joining us today. First, we have Gilles Larocque, Strategic Marketing Manager for the Aerospace Business Unit at Victrex. Gilles has been at Victrex since 2011 and has prior experience in the medical devices industry and as an R&D mechanical engineer consultant for the aerospace and defense sectors. Second, we have Petros Karapapas, technologist at Victrex. Petros is an aerospace engineer who has spent the past 15 years at the forefront of civil and military aerospace composite material and structure applications with a wide range of experience. For the past 2 years, he's been a member of Victrex's UK team, where he leads the development of materials and processes and progresses through technology readiness levels with aerospace customers. And third, last but not least, we have Peter LMPAEK, engineering manager at Victrex. Peter has been designing and engineering innovative composite solutions for 18 years with a wide range of experience in the industry. He currently leads a team of application design engineers in finding novel ways to leverage LMPAEK polymer and thermoplastic composites. So these presenters will give their presentation, and then there will be a Q&A session at the end. So attendees, you can submit questions at any time during the webinar in the Q&A field that you see on your screen. I'll also direct you to the polls tab next to the Q&A tab. There will be polls kind of presented throughout the presentation, so that will be where you go for that. And finally, one last note for me, that the webinar is being recorded and when complete will be made available to you via email from Composites World, so you'll be able to watch it back later. And without further ado, welcome Peter, Gilles, and Petros. It's all yours.
Okay, thank you, Hannah. So let's get it started. So first of all, about the agenda. So we have a pretty packed agenda where we will first have a quick introduction about Victrex and the advantage of PEEK and LMPAEK. Then we'll dive in with Petros on the fire protection and performances. Then Pete will go through the thermal runaway testing, and we'll have a final conclusion and a Q&A session. So quickly about Victrex. So as you can see on that slide, so Victrex, we invented PEEK. For those who don't know us, we invented PEEK about 40 years ago. So all we do is around PEEK and PAEK. We have the highest capacity in the world, a little bit above 7,000 metric tons of PAEK. We are well known to make polymer, to make granules, for sure, but that's not only what we do. We do also what we call product form, which is filament, some film, tape, and also parts. So for medical or industrial applications, so that we can be integrated as much as we can along the value chain. So we are split into business unit, obviously aerospace, also automotive, electronic, energy and industrial, and the medical group, which is called InVibio. So in a nutshell, Victrex is about 1,000 employees in the world. So we are deployed globally in every continent, America, Europe, and Asia. And yeah, all we do is around PAEK. So just to give some figures and highlight about where you can find PEEK. Again, you may use PEEK even if you don't know it today. But in automotive, we have more than 5 million gears used in application. If you are flying an aircraft, there's a chance that you have a piece of PEEK next to you. So we have about above 20,000 aircraft where Victrex solution are on board. Same for the medical application, quite a huge chunk of medical devices using Victrex or InVibio PEEK, more than 30 millions. Also for energy application, especially for oil and gas, where PEEK is used for seals. So as you see, quite a large number of seals using PEEK today. Same for electronic in terms of mobile devices where PEEK is included, more than 4 billions. And also the last piece of the puzzle about the manufacturing and engineering application, where we have more than 100 million machines using PEEK today. So just to give kind of some figures and range of idea what PEEK is used. So again, all we do is around PAK and PEEK, but for, PEEK, again, for those who don't know this pyramid, that's usually what we use to introduce PEEK. So that's the thermoplastic polymer pyramid. PEEK sits on top of the pyramid. This is why it's called a high-performance polymer. And we try to address key engineering requirements, and that's what you have on the right-hand side. So in terms of meeting extreme temperature, resistance, chemical resistance, hydrolysis, purity, it's bioinert, pretty good electrical properties. Obviously, it's a thermoplastic, so it's recyclable. The ease of processing it, pretty strong mechanical strength and wear properties. So what we used to say as a rule of thumb, if you are facing one of those issues, then PEEK can, if you are facing at least 3 of them, then PEEK can help, because PEEK rank, if not number 1, maybe 2 or 3 to address those needs. So pretty high demanding environment. So that's for PEEK. Today we'll talk about PAEK polymer. So again, maybe you're already familiar, but just in case, we used to say that it's like PEEK properties. So fitting or answering the same, let's say, problems, but with a lower melting point temperature and slower cross-linity rate. So just to give a high level overview, typically PEEK, the melting point is about 343 degrees. LMPAEK, which stands for low melt PAEK, so the LMPAEK polymer has a melting point 40 degrees lower, 3 or 3 degrees Celsius. And this may sound like a detail, but it's massive, and that opens up a lot the manufacturing windows, processing windows. And that's where we make the difference. So to do so, we are building what we call an ecosystem. So you can find LMPAEK on multiple forms. So as a filament for additive manufacturing, some compounds for injection molding, for instance, so also the tape, and that's what we will discuss in the next slides, on the film form, on the fiber form, and also on the part form. So just as a snapshot on the tape itself, so we have NCAM database already available on the NIAR NCAM website. So also it's all about high performances, processability, and versatility. So again, due to the lower melting point than PEEK, the resin flow for the during the layer process, also in terms of length without splice, the tape has excellent fitting characteristic, and overall the quality of the tape in terms of thickness and the width tolerance is also pretty high. And just to also illustrate, because we could spend the rest of the day just on that slide, but again, just to give the message from high level standpoint, that's what we call the value proposition of the LMPAEK UD tape, which has been quite adopted today in the aerospace world. So again, started with this pretty unique grade, and that's allow us, so which is LMPAEK obviously, but which allow us to make parts lighter, faster, better, and cheaper, because overall the objective is to increase the throughput for aerospace and also reducing the cost. So we can replace existing thermoplastic, potential part, thermoset, or even metal. And we are targeting 2 main applications. One is what we call the overmolding, which is like a small parts heavily loaded, so like we call loaded bracket. And also using the tape, we can, in terms of processing UD tape, so the UD tape layup, typically, let's say by additive, AFP, automatic fiber placement. So we can achieve pretty high speed, we can achieve pretty good quality. And so we are targeting like larger structural parts like ribs and beams, for instance. So that was really to give high level overview of what's LMPAEK, where we have a good fit and where we are today. So I think now the next section is about the fire protection performances. And Petros, I hand this over to you.
Thank you very much, Zil, for the introduction, and thanks to the Composite Gold team for hosting us. So, fire test. So, what are the fire test standards? I mean, practically speaking, in the aerospace world, it's two standards: it's the ISO 2685 and the AC 2135. One is from EASA, the European one. The other one is from FAA. Practically speaking, they are the same. So if you do a test and you pass one, automatically you pass the other. There are some subtle differences, but that's outside the scope. One thing that I would like to mention here is that until 2018, the test was done using propane as fuel. I think that had to do with how easy a lab would actually have access to propane and test with propane as the fuel. Since then, the change was done and we switched to kerosene. Even though the conditions like the flame temperature, heat flux, the time of the test, everything was the same. Using kerosene was actually made the test more severe because kerosene simply is a liquid as opposed to propane, which is a gas. So somebody then will say, okay, why do you do this test? This test is actually to determine the resistance to fire in what we call designated fire zones in an aircraft. This is not the fire or the heat that is coming out from the engine, from the combustion of the engine. So what's a designated fire zone? That usually are the areas which go around the engines or around the APUs, the auxiliary power units, which again, somebody can say an APU is also a small jet engine. So yes, that also is an engine. And also any other area that's actually designated by the designer or by the approving authority as a designated fire zone. So the reason why you would test is simply to demonstrate, first of all, that that the material is fireproof. That means that it has a place around an engine, it has a place in a designated fire zone, it has a place near an APU. And this is something that also, that data is then fed to the stress engineers and designers to say, yes, I can design something with this material and I can have it next to a pylon, I can have it next to an APU, I can have it anywhere which is next to an oil tank and an air oil heat exchanger, and I can have it there. So this is why we do these tests. Next slide, please, Zil. So the idea is that I talk about a bit the test, because again, it's a test which is common in the aerospace, but then again, it's only after you reach a certain level of maturity that you would like to go and perform this test. So practically speaking, you have a burner, the burner of a conical shape, and as I've said, the fuel is kerosene. So the temperature of the flame has to be 1100 degrees C or 2000 Fahrenheit for people that they don't use the SI system. Again, the heat flux density, again, it's how much energy goes into a specific area under a certain time. That the heat flux has to be of a specific above a specific value. And then you, practically speaking, you bring that burner in front of what you're going to test, and you start the test. The other test conditions, one is the airflow. So usually you have airflow, and then again, that's to simulate, an engine fire, because when you have a fire on an engine, on an aircraft engine, then yes, you're flying through the air, so some airflow is there. And obviously, if things go wrong, you also have vibration. And I'll come back to vibration because it plays a role. So the test procedure, it's rather simple, but it needs a lot of calibration. So you would actually turn the burner on, leave it to stabilize there for 3 minutes. Then what you do, as you can see there on the lower left hand of the picture, you would actually have type K thermocouples to make sure that your fire temperature is within the required range. So you do a calibration for 5 minutes. You do similar thing for the heat flux. The heat flux is doing by measuring You have a copper tube with water in, and you measure the temperature difference, and you know that make sure that you have the right amount of heat flux again coming through. Then the heat, the burner is moved into position. Again, the position of the burner is preset. Again, everything is in the standards, and you would start the test. The duration of the test is 15 minutes minimum. The pass-fail criterion for this test is simple. Is if the fire penetrates, if the fire goes through, and you have secondary or back ignition of the back face, this means that you have failed the test. So there are two important times for this test. The first one is 5 minutes. If nothing happens at 5 minutes and there is no fire penetration, you can then call your material being fire resistant. Then if more 10 minutes elapse, coming up to a total of 15 minutes, then your material is fireproof, assuming again, no fire penetration. When you finish the test, then we also do another round of calibrations, making sure, that again, the temperature was fine of the flame and the heat flux was fine. So you do a calibration before, you run the test, and you do a calibration after. During the test, what you can monitor is you can have cameras facing the front and the rear face of what you're testing. What you're testing can be a panel, or it can be a full structure. It can be anything depending on what you're going to test. And in our case, we also had a thermal camera. And the other thing that you do is you take pictures of the front and back face and trying to assess the damage. So next slide, please. So what we did, the fire test in our case, we used resonate testing. This is one of the few test houses that they can do the test in Europe, and it's a test house used by Rolls-Royce, GKN, NCC, Megit, you name it. And we tested several panels. So I'm only be presenting, the data from 3 panels here. The material that we used is the Victrex LMPAEK UD Tape. That's made with AS4 fiber, our polymer AS4 fiber. 143 that you see there, that means that's the GSM, that's the FAW, fiber aerial weight, and 34, that's the 34 is the nominal resin content. So we made 3 different panels with 3 different thicknesses. As you can see here, one was 20 plies, which came around to 2.27 millimeters or 0.1 of an inch. We had the thicker panel with 32 plies, around 4.4 millimeters thick. And we had also a 16 plies panel, a typical quasi layout. Again, just over 2 millimeters and being around 0.087 of an inch. The way that we make the panels, they were press consolidated. One of the most simplest ways that you can make a panel for thermoplastics. And when we did our tests, we tried to do it in as harsh conditions as possible. So we decided to have airflow off. The airflow, not only it can cool down the back of the panel, it also removes any volatiles. That's probably more relevant with thermosets, as thermoplastics don't have to have that volatiles as thermosets. And the other thing is, we also had vibration on. Vibration on the standard is around 50 hertz. And what the vibration does is quite common. When you do a fire test and your front face starts burning, then you produce char. And that char actually stays there and creates another protective layer. But when you vibrate, when you actually introduce vibration, and you're actually, it's like a shaker table that you have your panel on, that actually will produce enough forces for the char to fall off. So you are again exposing the next layer behind. What I'm trying to say is, with vibration on, you make the test, you're actually making the test harsher because you don't have that char layer being at the front face. So So we tested all these 3 panels, and I'm happy to say that everything passed. Yes. So even the thinnest panel, which was just over 2.2 millimeters thick, it passed the requirement, meaning that after 15 minutes there was no fire penetration. So again, we dive in a little bit into the details of the tests. So this is what we call the post-calibration data. If you remember, we said that before you start any test, you do the calibration. On the left, what you see is the temperature of the 9 thermocouples, type K thermocouples, and they have to be within a certain range, and obviously they have to, their average has to be 1100 degrees C or 2000 Fahrenheit. And then you can see there on the lower right how the thermocouples are placed. Again, the position of the thermocouples, the distance of the thermocouples, everything is set in the standard. So everything, so it's you have to adhere to the standard. Also, the type of thermocouples, how you calibrate them, everything is part of the test standard. And what you see just above the picture is the heat flux. The flat black line is what the requirement is, and then the green line actually shows the actual heat flux values that we had when we did the test. Again, everything within what it should be. And then let's see what the next slide says, please, Zil. So this is where you prepare the test. This is the panels. The panels, there were 525 by 525 squares. So this is around just over 20 inches, and you would put them on a frame, and where you see actually that's the front on the left, and what you see on the right is the back. I have highlighted here with a couple of yellow arrows. What you see is a cable. That cable is actually one of the thermocouples that we attach at the back. As you can imagine, because the temperature of the panels will go quite high, trying to stick thermocouples at the rear face, it's almost impossible. So the test house that we used, they have a way of having the thermocouple touching at the back of the panel. This is exactly opposite of the center of the burner, and they do that by having, where you see the central yellow arrow, there is a spring that actually pushes the thermocouple against the panel so as to make a measurement. So this is the picture. So this is where you start. This is where you start with the panel, make sure it's right. And this is what happens during the test. During the test, what you can see here is pictures. So you actually have feed from the front camera where the conical burner is, and you see the flames. And then you also have picture at the back. This is actually the most important camera, because that will show you if you have penetration and when was that happened, because again, there is a timer that's going on. At the bottom, what you see in red, this is the one snapshot from the thermal camera. The thermal camera, what it does, as opposing to the thermocouple, where the thermocouple that I talked in the previous slide, it's a spot measurement. The thermocouple, the IR camera, the thermal camera, is an area measurement. And the graphs that you see on the right, the top one is the vibration, making sure that the vibration is at 50 hertz or 4 Gs, in our case, depending on the mass of the panel. So it had to be around 4 or 4 point something Gs. And what you see at the bottom, this is exactly what I talked before in the previous slide. This is the temperature of the rear facing of the thermocouple that's at the rear face. Everything is in Fahrenheit, and you can see we start around room temperature, and within five minutes or so, we get up to 800 or 900 F. Next slide. This is the slide where hopefully it will work. We have the fire test video. So we compress the 15 minutes into 1 minute. You can see the burner coming there on the left, and the fire test starts. In the middle is the IR camera, and on the right is the rear face. You can see how the rear face actually swells as the temperature, of the fire attacks the panel. For those that they have done fire tests, they will tell you that anything interesting will happen in the first 3, 4, maximum 5 minutes. Usually, 99% of the cases, if nothing happens in the first 5 minutes, I mean, no fire penetration, no volatiles, no secondary burns, or anything like this, usually the system comes into equilibrium. So this is what we saw here. Again, 1 minute, 15 minutes compressed into 1 minute. So, and then after the test, just before we dismantle everything from the frame, we take pictures. So you can see here the front face, how the front face looks, how the fire has eaten, allow me to say, part of the panel. No fire penetration though. So that's the front face. And we also, on the next slide, we have the pictures from the rear face. Again, in yellow, I have have highlighted, the thermocouple, and you can see how this panel, has some swelling, but again, no fire penetration at the rear face. Next slide. Yes, as I mentioned on the early slides, we start with the calibration, we do the test, and then we finish with the calibration. So this is what we call the post-test calibration data. Again, on the left is the data from the 9 Type K thermocouples, making sure that everything again falls within the upper and the lower limit, but also the average is actually where it's supposed to be. And then on the right is the heat flux. The black line is the minimum requirement. The green line is actually what we achieved during the test. And next slide, please. So to sum up, we tested 3 different panels. The layup, I have the layup here. The layup doesn't play an important role when it comes to fire. What is actually of importance is your matrix material and your fiber and the thickness. These are the most contributing factors, whether you pass or fail at the fire test. So we had a typical quasi-laminate of 16 plies that was around 2.2 millimeters thick. And what I have actually said here is the fire temperature is 1100 degrees C or 2000 Fahrenheit. So this is what you have at the front face. You start with 2000 Fahrenheit or 1100 degrees C, and at the back of a panel, which is 16 plies, just 2.2 millimeters thick, the maximum recorded temperature was 434 degrees or 994. So just to put this in perspective, you start with something which is 2000 Fahrenheit, and you are, after 2.2 millimeters of material, you go down to almost 1000. So you have a 50% reduction of the temperature. That was for the thinnest panel of 16 plies. Then we did another one, double that thickness again. So we go from 1100 degrees C to 410. Then we also had the ply panel, which was in between those two with 20 plies. And again, similar results to the previous one. From one side, I have the fire, which is 2000 Fahrenheit, and I go down to 789. On the last column, what we have recorded, but this is also actually work still going on, is how many plies actually we lost. So what I'm trying to say is, I started with a panel that was, a perfectly manufactured panel that had 16 plies. So after 15 minutes of fire at 1100 degrees C, the fire went through 7 plies. So I lost 7 out of my 16 plies. I'm saying this because this is something that, depending again on the fire designated zones that I mentioned in the first slides, this is important because depending on what you're making, what you're manufacturing, where that sits on an aircraft engine, that's important because there are requirements for some structures to also have some post-fire integrity, structural integrity. So that's why I have it here. It could be of interest to the audience. Just to mention then, on the thicker panel, which was 32 plies, only 5 plies, they were damaged, which makes sense. The thicker the panel, the less damage you will have through. And then this is my one of my last slides. So we talked about fire and testing UD tapes that have fibers. Another important aspect of when you do a fire test is what type of fumes actually come out when a fire is burning. Because it's one thing, having something that the fire doesn't go through, which is very, very important, and having its structural integrity. However, what is also of importance is what happens to that fire. I mean, is that fire toxic? Again, because having in mind that these materials go into an aeroplane, so it's quite common that what we have listed here is some tests that we did on the polymer, on the LMPAEK polymer. So we would either make a plaque or films, again depending on the standards. We tested again the Boeing standards, but similar to the case with the fire test standard, whether it's the Boeing standard or the Airbus standard, AITM standards, they are interchangeable. So when you pass one, you pass the other. So we tested the rate of heat release. It's also called as OSU. I think it comes from the Ohio State University. Again, to see how much heat goes through. The other 2 important tests are the vertical flame. So this is the 60 seconds and 12 seconds. What you do here is you have a strip of material of a certain thickness and you burn it, and what you measure is a couple of things. You burn it for 60 seconds, and what you are after is to see when you remove the flame, for how long does the polymer still burns, and there is a requirement not to be above 15 seconds as far as I remember. Excuse me. The other thing that you could test is the flame, how much the length, how much actually of that specimen was burned, and then if you have any dripping of that polymer, if it extinguishes within 3 seconds or no. Then another test is the smoke density and combustion toxicity, whether it's flaming or non-flaming mode, whether it's still during the flame or after the flame has been extinguished. And what you do is you measure what particles, what chemical elements you have there in the smoke. So practically speaking, you want to know, can I see through the smoke density, and is the smoke toxic, yes or no? And in all our cases, our polymer passed with flying colors. So not only have something which can withstand fire, also doesn't produce any toxic fumes, and again, this also opens the door, allow me to say, for applications that they are suitable for aircraft interiors, air mobility, you name it. Next one, please. Yeah, and that's my summary. So we tested against the AS AC20-135, the FAA standard, which is practically speaking is equivalent with the ISO standard. We tested 3 panels, 3 different thicknesses. Everything passed. Our material is fireproof. The minimum that we tested is 2.2 millimeters, the thinness that we passed. And this is important because it opens up the application for engine, propulsion systems, APUs, and also if you combine that with flame and smoke and toxicity data, that gives an ecosystem. But also, there is another interesting fact when you add it to the equation is, how battery thermal runaway tests. But I will leave that for my colleague Peter to give you more details on that.
Thanks, Petros. So I'll be speaking about some thermal runaway testing that we did. And this is really a pre-qualification test to assess the suitability for the material for further investigation. And that's a lot of words, but it's a long way of saying, is it worth putting any more money, time, and effort into investigating this as a potential battery enclosure material? So what we did is we worked with Forward Engineering, who had developed a test for automotive. And this test was codified by UL. So it's a standard test now. And what it does is it places a 5x5 array of lithium-ion batteries inside a steel box. The steel box has one open face where we can swap in and out different material combinations. So in this picture here, we've got like a tan test sample that were a bunch of different composite sheets that we swapped in. And that is basically the barrier that we're going to be testing and looking for any flame, smoke, toxicity, ejecta, or anything else making its way through that membrane. This test, it's typically conducted at a few different pressures. The green cylinder is basically a calibrated orifice that allows for different pressures. We ran this at 2,500 kPa, and that was sort of what was recommended to us by Forward Engineering as the most applicable to the environments and the arrangements that these materials might see in a lithium-ion battery. Next one. So here's a picture of the actual test setup. You can see the steel box and you can see the basket of batteries there. There's some coupling connectors for the thermocouples that are attached to the batteries throughout the inside of the box, as well as the inside of the composite sheet. In the right-hand image, you can see I've circled or sort of highlighted two cells in the middle. And with these what's going on with these is that the wrappers were removed from the cell. You can see they all typically have like a greenish shell to them, but those wrappers were removed and a resistive film heater was applied. That resistive film heater is what sort of builds up heat, and it's that sort of heat blanket around the battery, which then triggers the thermal runaway. So that temperature was recorded via thermocouples to monitor inside the box as the heat is applied, and then as it starts to run away. And then you can see the other exit for the orifice for the pressure monitoring. Next one. The materials we tested, they all are based on Victrex's LMPAEK polymer. There were a few different material combinations that we went with. The first being a unidirectional tape. We use Hexcel's AS4 UD carbon fiber for that. It's a 143 GSM, 34% resin content, unidirectional, so a pretty standard aerospace material type. It's just over 1/8 of a millimeter thick per ply. We make the tape in the UK, and the laminates that we tested here were 4, 8, and 10 plies thick. The next one was a 7781 glass weave from Ensinger. It's their Tech PAEK GF50 product, and again, that's got Victrex's LMPAEK polymer. It's an 8 harness satin weave. It's about 1/4 of a millimeter thick. So then we went with 4, 6, and 8 plies thick on that. Lastly, as a bit of a curiosity, we had a little bit of time and left over, and simply stacked some UD plies with some glass plies, not consolidated, but just stacked them together in a combination to see what would happen. And in this case, we had the glass facing the battery cells and the carbon on top. Next one. So this is a typical I guess, summary of what's going on with the various thermocouples. But what I wanted to show here is that this actually has data from 3 tests overlaid on it. And the gold lines, those are showing what's going on with the temperature at the trigger cells. Those are those 2 batteries that had the jackets removed and have the sort of heat blanket surrounding them, the ones that trigger the event. And then the red TCs are the enclosures. But you can see whether it's a solid line, a dashed line, or a dotted line. All of the results, I mean, there's a big range in there, and these are all the same setup, same basically the same test run 3 times sequentially. So it's pretty important to run this test multiple times for any given configuration to see really what's going on with the range of outcomes. And note that in the sort of gold oval there's one particular test, the dash test, that had a funny event going on, and there's a bit of a knee or a bit of a bump in the temperature profile there, and you'll see that in the results in a few more slides. But basically, what's happening there is there's a delay between the runaway that's happening from the first trigger battery to the second trigger battery. So, unlike the tests that Petros was just summarizing and describing, this one, you're really sort of trying to generate a bit of an explosion, and in the most controlled way possible. So, it doesn't always go to script, but that's why you do three in a row. Next one. The bottom of this slide shows that same timeline as on the previous slide, but we've stretched it out a little bit and tried to overlay it with what you'll see in the video in a couple of minutes. But what's happening is in the early stages, you've got the trigger cells being heated up, and that the resistive film inside the battery, the one that separates the cathode and the anode, is being eroded. So the outside jacket is heating up the battery, and then eventually the barrier between the anode and the cathode fails, and inside the red section here in the middle is where you've got essentially the runaway event beginning. It sort of builds upon itself, and then it reaches sort of a maximum point where you've got maximum temperature and pressure generating the sort of cascade of events throughout the rest of the battery array inside the box, and that's your maximum release of energy. The rest of the time is being spent really testing the ability of the material to survive dissipation and containment of that energy. So, the first 2 sections here are build up to the trigger point, trigger the event, trigger the sort of catastrophic battery failure, and then the rest of it is contain and dissipate the energy. Next one. So we'll press play on this in a second, but what you're going to see is sort of those 3 phases: the breached cell barrier, the thermal runaway, and then the material surviving. So go ahead and hit it. Here we are. We've breached it, or we're heating it. We've breached it. Thermal runaways happened, and now the material is being heated, pressurized, and there's also ejecta on the inside. So it's fairly short video, you can see there's a lot of energy coming out of the metal box. Eventually the TC comes off, but the material itself doesn't fail. And, you know, you saw a lot of energy coming out of the vent on the box. It's done in such a way that the orifice will basically only allow about 250 kPa of pressure to build inside the box. But the material survives because through sort of the window of composite that we're looking at, there's no smoke venting, there's no flame, and there's no ejecta. So, you know, it is a bit of a different test from what Petros was describing, in that, you know, this is a pressurized environment, and there's ejecta, or essentially projectiles of decayed battery hitting the inside of the composite. You can go next. So I'd mentioned a couple of times that there's essentially a pressure limiter between, or that caps the internal pressure at about 250 kPa. And that's where a lot of, you know, our results lived. There's, of the LMPAEK tape, UD tape samples in blue, 2 of the tests happened sort of right there and below the line of 250 kPa. Over there in the orange, the glass fabric, there's actually 2 dots quite close together just above the line. And then the unconsolidated glass and UD was also sort of in that neighborhood of under 250 kPa. But if you think back to the that slide that had the bit of a knee, or the bump in the curve, that where the battery cell was failing, and the trigger cells were failing, there was a bit of a lag between cell 1 and cell 2. And in that particular test, the peak pressure measured was actually about 824 kPa. So a significant bump, significantly higher than the other tests, but passing nonetheless. We did test a number of additional configurations, but those were all thinner. So I'd mentioned that we did 4, 8, and 10 plies for the UD. The 4 and the 8, they did fail. They did have something going through the laminate, whether it was smoke or flame. Similarly, the thinner glass laminates that we tried, the 4 and the 6, also had that. Next one. So here's kind of a picture of a couple of pictures of what they look like after testing. And in each image, you see the visible side to us during the test on the left, and then the side that sees the heat on the right. And in each one of these, you know, you see a bit of charring, and you see, you know, if you could zoom in and look at these or hold them in your hand, you would see some ejecta from the decayed battery embedded in these. So it's a pretty violent test, pretty aggressive test. But this is what passing looks like for all of these various material combinations. If you look closely, you might see some cracks, or maybe some deep grooves, maybe some areas where polymer has, you know, completely eroded. But generally speaking, these are all good results. Next one. So no conclusion slide there, but the conclusion is that we found these do merit additional resources and additional analysis, because the results were good. And we found that the material combinations and architecture of those coupons did yield good results and passed the test. So those were fairly generic, but application specific geometries and material combinations, it's probably worth taking a look at.
Okay, thank you, Pete. So just conscious of my time, I just have a few slides for the conclusion, so I'll move on, take it from here. So as a conclusion, we just wanted to highlight quickly the ESG activity at Victrex, because all what we try to do is to make part lighter overall, to reduce, especially for aerospace, the CO2 emission. So just keep this in mind. If you want to take this offline, we work a lot on this topic, which is more or less linked also to what we've been just discussing. But specifically about this presentation today, so the key points we need to take away as a takeaway is really about the LMPAEK polymer, like that meets the aerospace standard for fire and flame resistance, promising results after thermal runaway testing, and that's definitely opened the door for new application for engine propulsion, commercial aerospace, but also e-mobility. So just also as a side note, there's a few conferences coming up soon. So if you want to follow this up, we have ITEC in Bremen, Germany, also Fakuma, where we will share some great news about LMPAEK, and finally, which is a long kind of since a few months though, but obviously JC, where we'll be attending and happy to discuss further about this topic. And I think that's the last slide. Now it's opening up for Q&A, I guess.
All right, sounds good. Thank you all. That was a great presentation. So like Gilles said, we have a few minutes for Q&A now. So attendees, if you have a question, now's the time to put it in the Q&A box. We'll start with some we've already got and get through as many as we can. So the first question goes back, I believe, to one of the tests that Petros was talking about. Asking about the strength, can you speak to the strength properties that the panel would have during the burn test that you talked about at elevated temperatures?
There is no I mean, you can assess what's the strength, what strength has remained, but the fire test is agnostic to the strength. The strength is something that you could do if you are like an aircraft designer, a tier 2 or tier 1 or a stress engineer. And the simple way of doing that is, especially for the quasi panel, for instance, which was the thinnest one, what you can do is you can actually test it before in tension and compression. So you can have your strength and modulus values, and then you could go and do the fire test and say, okay, now and test them again. So you can see, what the drop-off is. Again, practically speaking, and if I can use a very, very quick, quick and dirty calculation, for my quasi panel, I almost lost half of the panel, during the fire. So somebody could say, it's going to be half of the strength. But again, that has to do with what you are testing, which panel configuration, et cetera, et cetera. So this is usually a test or a post-fire examination or test that you would be doing when you are the design, you have the design authority and the manufacturing authority of making those parts, and not to us, which we are the material supplier and the material developer.
Okay. Great. The next question asks, what is the minimum thickness of a laminate that would pass the flammability test? And also, have you performed cabin safety testing using specimens? Specifically made with additive manufacturing filaments. We're getting more specific here. But...
Well, the minimum thickness that we did was 2.2 millimeters. And that was based on the 16 plies laminate that we made. If I'm honest, I could possibly go thinner. Yes, I could go thinner and go down to like 10, 12 plies, which would equate to something like 1.82 millimeters. One of the reasons that when I was making the parts I didn't go is because because goes actually back to the previous question. How many structures you're going to have that they're going to be less than 2 millimeters, that they're going to be there, that they're going to be taking loads, and they're going to be structural parts that are going to be sitting around the engine, that they're going to be less than 2 millimeters. So that's why one of the reasons that we didn't do the test, or at least for the first round of tests, we have, in the new year, we actually it's on the cards actually to go and see how low we can go. Allow me to say. And what was the other part of the question, Hannah?
They asked also, have you performed any cabin safety testing using specimens made with additive manufacturing filament?
No, but the only thing that I can say, and I can say that with high degree of confidence, is that our 3D printing filaments are made out of the same polymer. So as I've showed in my slides, the polymer passes vertical flame, smoke, toxicity, heat release, and everything. So I don't see why the 3D filament, which is made of the same polymer, that wouldn't pass the same tests.
Okay. So obviously you guys talked a lot about your low melt PAEK. One question, do you have a high melt strength PAEK?
It's the standard PEEK. It's not. It's the standard PEEK that Zil was talking about. PEEK is what is actually the common for aerospace, which was the standard, and then we invented and developed and qualified the low melt. So you have your standard PEEK, and then what we call low melt. Also, LMPAEK is also known as low melt PEEK. Zil, anything that you're going to add to this? Give it your spin.
No, that's the grade we have. This is it. Yeah.
Great. Next question. How do the material's fire protection and thermal properties impact its integration into composite manufacturing processes?
Is that with me or you, Peter? I mean, what I can say, and then I can pass it on to Peter, is that it doesn't affect. I mean, what you actually know is, that when you're designing a structure, you also have the fire protection and the thermal protection. Whether you need it or not, that has to do with what you're designing and where that part that you design will go. It's going to be sitting next to an engine. Is it going to be a battery box? So again, what I'm trying to say is that what we've presented today, it gives you more flexibility to have our materials closer to danger zones, whether these are heat, fire, flame, or thermal runaway. Peter, anything that because you're more experienced in manufacturing than I am, especially with thermoplastic. So
yeah, I mean, you're right. This sort of qualifies it to be in the application, but then as in terms of manufacturing, it doesn't change how you might make the part. But once you know that it is potentially a good use and applicable, then that's when sort of the application-specific testing might take over and answer some of those questions about strength and stiffness, after an event, during an event, kind of thing, for a given part design.
Okay. We're getting to the top of the hour. We'll grab one more question here. This one's about standards. What fire safety and performance standards are relevant to the use of these tapes in high temperature environments?
Well, it's one to rule them all. Allow me to say it's the FAR 25853, which is the FAA, and again similar numbers. It's the JAR for the European and the CCR for the Chinese. This is where actually everything is documented. That's a standard that started in the 50s, 60s, and updated in the 80s to also include aircrafts that they are actually down to 20 seats. And it documents everything. Again, there is the ABD 0031 for Airbus, or the BSS 7 series for Boeing, that they have everything. And if somebody wants to really learn about the fire testing, then there is a document publicly available by FAA, which is called Aircraft Materials Fire Test Handbook. And there it goes on how you do the test, on how you test structural parts, interior parts, wires, acoustic insulation, you name it, everything. So what we did actually, they are parts of these, Bibles of fire testing in the aerospace.
Okay. Excellent. So we have reached the top of the hour here and the end of the webinar. We do have a few questions that we weren't able to ask live. These will be forwarded to the Victrex team so you can answer later. Thanks so much to all of our presenters for the presentation today. That was great. We really appreciate it.
Thank you.
Thank you.
for having us.
Thank you for having us.
And thanks, of course, to our attendees for joining us today. Visit compositesworld.com for more information on the next webinars.